What specific problem does your proposed method aim to solve regarding transformer models and their search capabilities?
The proposed method aims to address the limitations of transformer models in performing search tasks, particularly in the context of directed acyclic graphs, DAGs. It investigates whether transformers can learn to effectively search for the next vertex along a path from a start to a goal vertex when trained on a carefully constructed distribution of search problems. The method emphasizes the importance of eliminating heuristics that could hinder the model's ability to learn a robust and generalizable search algorithm. By generating a diverse set of training examples with varying look-ahead parameters, the approach seeks to enhance the model's search capabilities, demonstrating that transformers can achieve high accuracy in search tasks when provided with the right training data. Ultimately, the research highlights that simply increasing model size does not inherently improve search performance, indicating the need for alternative training strategies.
Can you describe in detail how your proposed method works? Illustrate the algorithm step by step, particularly focusing on how the transformer learns the search task in directed acyclic graphs, DAGs.
The proposed method for training transformers to learn search tasks in directed acyclic graphs, DAGs, involves several key steps. First, we generate a large number of search problems by creating DAGs with a start vertex and a goal vertex, ensuring that the model's task is to output the next vertex along the path to the goal. We utilize a carefully constructed balanced distribution to generate examples where the look-ahead parameter, L, is uniformly distributed, preventing the model from relying on heuristics. During training, the transformer processes the input graph and, through its layers, simultaneously computes reachable sets of vertices, effectively extending these sets at each layer. The mechanistic interpretability analysis allows us to reconstruct the computation graph, revealing that the model performs path merge operations to combine reachable sets, thereby learning a robust search algorithm that can generalize to various graph sizes and complexities. This step-by-step approach ensures that the transformer not only learns to search effectively, but also retains the ability to adapt to unseen graph structures during evaluation.
Can you provide a simple illustrative example that demonstrates the inner workings of your proposed algorithm? Walk through the main algorithm steps with this example.
To illustrate the inner workings of the proposed algorithm, consider a directed acyclic graph, DAG, with vertices A, B, C, and D, where A is the start vertex and D is the goal vertex. The edges are defined as follows: A right-pointing arrow B, A right-pointing arrow C, B right-pointing arrow D, and C right-pointing arrow D. The algorithm begins by initializing the reachable set for each vertex, starting with A, which can reach itself. In the first layer, the algorithm identifies that from A it can reach B and C, thus updating the reachable sets to include A, B, C. In the second layer, the algorithm extends the reachable sets by checking the edges. From B it can reach D, and from C it can also reach D. Consequently, the reachable set for D is updated to A, B, C, D. This process continues, with each layer allowing the model to merge reachable sets, effectively doubling the number of reachable vertices at each step. The final output is the next vertex along the path to the goal, which in this case would be D, demonstrating the algorithm's ability to perform a search through the graph by systematically expanding reachable sets.
What specific advantages does your method have over previous approaches for training transformers to perform search tasks?
Our method offers several specific advantages over previous approaches for training transformers to perform search tasks. Firstly, we utilize a carefully constructed balanced distribution that ensures the training examples require the model to engage in deeper search processes, effectively preventing reliance on shortcuts or heuristics that hinder learning. This contrasts with earlier methods, such as the naive distribution, which often resulted in low accuracy on larger look-ahead tasks due to insufficient exposure to complex examples. Secondly, our mechanistic interpretability analysis allows us to reconstruct the computation graph of the model, providing insights into the specific algorithms learned during training, which was not a focus in prior studies. Additionally, we demonstrate that our approach enables transformers to generalize to unobserved look-aheads, showcasing a robust learning capability that previous models lacked. Finally, by employing streaming training, we simulate a vast corpus of data, enhancing the model's ability to learn effectively from diverse examples throughout the training process.
How did you validate and test your method? What experimental design, datasets, and metrics did you use to demonstrate the effectiveness of your approach?
To validate and test our method, we employed a systematic experimental design involving 3 distinct distributions of directed acyclic graphs, DAGs, naive star and balanced distributions. We trained transformer models on these distributions, ensuring that the balanced distribution specifically prevented the model from relying on heuristics, thus allowing us to evaluate its ability to learn robust search algorithms. The effectiveness of our approach was demonstrated by measuring the model's accuracy on held-out test sets from each distribution, particularly noting that the model trained on the balanced distribution achieved near-perfect accuracy across various look-ahead parameters. Additionally, we conducted mechanistic interpretability analyses to reconstruct the computation graphs of the trained models, allowing us to identify the specific search algorithms they learned. Metrics included training accuracy, test loss, and the proportion of path merge operations identified, which provided insights into the model's search capabilities and their generalization to unobserved look-aheads.
What were the key results that you achieved with your new method, and how do these results compare to existing solutions in the literature? What does this indicate about the method's practical applicability?
The key results achieved with our new method include demonstrating that transformers can learn to perform search tasks on directed acyclic graphs, DAGs, when trained on a carefully constructed balanced distribution, achieving near-perfect accuracy across various look-aheads. Our mechanistic interpretability analysis revealed that the model performs search simultaneously on all vertices, utilizing a path-merging algorithm to extend reachable sets, which contrasts with existing literature that indicates transformers often rely on heuristics and struggle with larger graphs. Additionally, while previous studies showed that increasing model scale does not necessarily improve search capabilities, our findings suggest that a well-designed training distribution is crucial for effective learning. This indicates that our method has practical applicability, as it provides a framework for training transformers to robustly handle search tasks, which is essential for more complex reasoning problems. Overall, our results highlight the importance of training distribution over model size in enhancing the search abilities of transformers.